starting with surfaces. Start with the cylinder. I typically think of a cylinder. What shape do you think of? Glass, can, your bottle. That's a special type of cylinder called a right circular cylinder. In general, this is the definition of a cylinder. It's just a set of parallel lines passing through a given curve. So there's our typical cylinder, the right circular cylinder. However, that's also a cylinder. That's just a cylinder turned on the side. Again, that's pretty typical.
It's a right circular cylinder, like half instead of equal.
No, right circular cylinder just means that its base, cross sections are circular, and the rulings are perpendicular to the actual side itself. And this is also a cylinder, as is this. They're all cylinders, by definition. So once again, we're lied to in geometry. The idea of a quadratic surface, this is just an extension, if you look at it in Calculus 2, of the, what do they call it? Conic sections. We just add the third variable. And the general equation itself is the same. It's just a surface that has an equation that is a general 3-variable quadratic. And the next set of slides, I recommend you print out. And that's going to give you a listing of some of the most common quadratic surfaces. I might even include those on the exam. I might just make a separate table of them and upload them for you to print out. That's all I want to do with surfaces. I don't really want to delve too much into them. So you will be asked questions to be able to identify a quadratic surface. That's why I would recommend these set of slides. This is what I really want to get into. Again, we're extending our discussion from Calc 2. End of Calc 2, you should have learned polar coordinates, the polar coordinate system. That is an alternative coordinate system in 2 dimensions. We're extending this now into 3 dimensions. There are 2 in particular that we want to look at. Cylindrical coordinates and spherical coordinates. There's another one that's commonly used, hyperbolic coordinates. We're not going to study those in this class. I think you do, if you take a college geometry course, I think that studies the hyperbolic system as well as the spherical system, and maybe some others. It's really a study of non-Euclidean geometry. So cylindrical coordinate system, point is represented by the word r theta z instead. R theta is your common ordered pair in polar, and obviously z is just z. So it's just polar coordinates, and you add the z-axis. That's it. So if you're familiar with polar coordinates, cylindrical is no problem. Spherical coordinates. Is the universe flat? What's the shape of space-time?
Curved.
Circle. It's curved. Specifically, how is it curved?
Sphere.
It is a sphere. We should never be looking at Euclidean geometry then. Euclidean geometry is a lie. It's working in spherical. The base of general relativity too, by the way. Everything's done in spherical coordinates, which is fun. It's represented by an order triple rho theta phi. Rho is distance from the origin to the point. Theta is just the angle that's used in cylindrical. Phi is the angle formed by the segment OP with the positive z-axis. When finding theta, what you're really doing is you're just looking at the projection of your point onto the xy plane. And then you find the angle that the line segment O to that projection makes with the positive x-axis. Important to note, phi here, 0 pi. It's also referred to as the angle of declination. And rho typically non-negative.
Is it the same as the azimuth angle?
As what?
Azimuth angle?
I'm not too familiar with that. So maybe. It does sound like something that's used in astronomy. And we have our conversion factors. Being able to convert between, or really being able to convert from rectangular to either cylindrical, spherical, extremely important later. Also being able to convert rectangular to polar will also be important. That's kind of what we're focused on, converting points and sets of points. Right now, just a single point. We'll look at sets of points a little bit later. First, they want to go cylindrical to rectangular. Okay, well. So here we go. Okay, well, there's our list, cylindrical to rectangular. X equals r cosine theta, and remember, order triple is r theta z. X would be 3 cosine pi over 4.
With like 5 or 4.
Should be pi over 3, because I saw 4. What's cosine pi over 3?
1/2.
Correct one is 3 halves. Y is r times sine of theta, right? 3 times sine of pi over 3. What's sine of pi over 3? Y coordinate is 3 root 3 over 2. Oh, this is the hardest coordinate. Z equals Z. So in cylindrical, your Z coordinate doesn't change. Let's say this is a piece of R to represent rectangular. That would be a point in rectangular. It's very straightforward. Rectangle to cylindrical. R is given by the relation r squared equals x squared plus y squared. The reason for this is, technically speaking, r can be negative, theoretically. Practically, we never take r to be negative. I don't even like that they allow r to be negative. The definition of r is a length. Four and four, 8. Makes r root 8, right? How does that simplify?
2 root 2.
There's your radius, 2 root 10. Theta is given by the relation tangent theta equals y over x. Two over negative 2. What is the inverse tangent of negative 1?
3 pi over 4.
What's the range for inverse tangent?
It's negative pi over 2 pi over 2.
So what's the inverse tangent of negative 1?
Negative pi over 2.
Minus pi over 4. Is that the angle we're looking for? No. There are two problems with that angle. Generally speaking, we will take theta to be between 0 and 2 pi, though that's not an actual fixed requirement. The biggest issue is negative pi over 4 is located where? In what quadrant? Where is our projection of the point located? In the second quadrant. So it's not just the inverse tangent. You're correct, the angle is going to be 3 pi over 4. But it's not the inverse tangent. Get to add pi to it. Not that big of an issue for a problem like this, because you can easily determine the angle from the unit circle. Not all points are going to be a simplification where you may get something like the inverse tangent of negative 2/3, which doesn't have a nice angle. So being able to logic your way out this way, pretty important. And of course, z just equals z. And so our point in cylindrical two root 2, 3 pi over 4. Pretty straightforward, right? All right, spherical to rectangular. X is rho, cosine theta, sine of phi. And the first person to call that a P fails the class. Again, order triple and sphericals in the order rho, theta, phi. What's cosine of pi over 4?
Sorry, it's just a general question. What does it mean to convert a spherical point into a rectangular? Like, what does it mean to?
You're given a point in spherical coordinates. You want that point in rectangular coordinates.
Also, just converting it.
What was cosine of pi over 4?
Sorry, the one. Cosine, sorry, root 2 over 2.
What's sine of pi over 6?
Half.
Real quick. What does that simplify to? Took too long. Two or two. Y is rho sine theta sine phi. What's sine of pi over 4?
2 over 2.
And of course sine of pi over 6. So how does that simplify?
2 over 2.
The same thing. Z. Rho cosine phi. What is cosine of pi over 6?
3 over 2.
How does that simplify? No. Uh-oh. What's half of 8? 4. 4 over 3.
Are these just the definitions, like p cosine, theta, sine?
Oh, look. You're the first person to call it P.
Oh,
Oh, that's an easy grade.
wait, what is it?
That's rho.
Oh, rho.
The Greek letter rho.
Sorry. Anyways, rho, cosine, theta, and sine of the other one. Like, are these all like definitions?
Those are the conversions. They are derived in the video.
In what video?
I post videos on Blackboard, the lecture videos.
Oh,
I just present them in class. The derivations, the full derivations are provided in
okay.
the video. That would be the point in spherical coordinates. 2 root 2, 2 root 2, or I'm sorry, in rectangular, sorry. That'd be the point rectangular. 2 root 2, 2 root 2, 4 root 3.
And are all these different parabolas going to be on the exam?
Hmm?
Are all these different long enough with all of them, then go to the exam.
Rho is given by the relation rho squared equals x squared plus y squared plus z squared. Again, it's given by that because theoretically, rho can be negative. Practically, we're always going to take rho to be non-negative. Once again, it's measuring a distance.
So is that y squared? In case it's negative, making like a positive line.
To satisfy the equation of the sphere. What's 2 root 3 squared? It's 12. What is 6 squared? Add to 12. Negative 4 squared. Add to 48. Square root of 64. Rho is 8. Tangent of theta, so theta is given. Tangent of theta equals y over x, right? Theta is the same angle as in cylindrical. Which quadrant are we in? First quadrant. Theta is just the inverse tangent. 6 over 2 root 3 simplifies to what? Which is the same as root 3. What's the inverse tangent of root 3?
Root 3 over 3.
Inverse tangent of root 3. Root 3 over 2 divided by 1/2 is not root 3. How is tangent defined in terms of sines and cosines? What angle is sine equal to root 3 over 2 and cosine 1/2? So what's the inverse tangent of root 3? inverse tangent of root 3? What angle did you just give me?
Root 3. Or sorry, pi over 3. Oh,
That's the inverse tangent of root 3. Phi is given by cosine of phi equals z, and there's often two ways of seeing it written. I write it this way for simplicity. Z over rho. Technically, since rho could be negative, it's z over the square root of x squared plus y squared plus z squared. Cosine phi is negative 4 over 8. What is the range of the inverse cosine? Pi is in the range, I agree. At 0 pi,
Oh, that's the pi map.
what could phi be? Pi is just a single value.
No, but obviously from the origin.
That's not always obvious. What did we say phi could be? What values? You can always just take the inverse cosine. That requires no thought. What's the inverse cosine of negative 1/2?
negative.
Inverse cosine of negative 1/2. It's an angle.
Oh, 2 pi over 3.
That'd be the point in spherical. 8 pi over 3, 2 pi over 3. You're given a curve. What's the actual definition of a curve? It doesn't have to be a curve either way. So curve is just a 2-dimensional. Solid would be 3-dimensional, but the idea is the same. So we'll start with curve and we'll extend that. What is the actual definition of a curve?
Would it just be a line?
A line is a curve.
Not a straight line.
That is redundant. Lines are by definition straight.
But a curve isn't a straight line.
Exactly. Doesn't have to be. Our general definition of a curve is really just a graph. Curve is a set of points that satisfy a given relation. So the unit circle is the set of points that satisfy x squared plus y squared equals 1. Surface is the same. It's just the set of points that satisfy some relation. I'll just go with x squared plus y squared equals 1. This is the unit circle. How many points are on the unit circle?
Infinite.
Well, what we want to do is convert a set of points between coordinate systems, not just a single point. Right. Relation, curve, same thing. Curve is just the graph of a relation. Relation x squared minus y squared equals 25. That is in rectangular. It's known as a rectangular relation. You want to write that as a cylindrical relation. Well, x is r cosine of theta, isn't it? Y is r sine of theta. Right, square both terms. There's a common factor, isn't there? That can be simplified. What's cosine squared of theta minus sine squared of theta?
Well, 2 theta.
Cosine of 2 theta. Sum is 1. R squared cosine of 2 theta is 25. That would be acceptable. That's fully simplified. However, sometimes they will ask you to write the relation in the form of R equals a function of theta and z. I'm going to continue. Divide both sides by cosine of 2 theta, which is the same as multiplying by secant of 2 theta. R would then be 5 times the square root of secant 2 theta. Oh, by the way, we don't need to specify any restrictions here, because there are none. Secant of 2 theta would never be negative. Why?
Steady.
Why do we know that secant of 2 theta is never negative?
Because it's under square root.
I'm putting it under square root because I know it's never going to be negative.
Up to the radius. Or what is the radius of the body?
Again, theoretically, not really.
2 theta and,
2 times pi over 4 is pi over 2, cosine would be negative there. Which means secant would be negative. Even though before that. By the way, that actually should have been 25. I don't know why it was written 5. Before you even multiply by the secant theta, just look at the r squared cosine 2 theta equals 25. What do you know about r squared? It's always positive because you're squaring it. So even if you allow for r to be negative, r squared is still positive. R squared times cosine has to equal what?
25.
Which is positive. There's only 2 ways you can multiply 2 numbers and get a positive. They're both positive or they're both negative. Since r squared can never be negative, that means cosine can never be negative. Meaning secant can never be negative. So I can just safely take the square root because I know that that secant 2 theta won't be negative.
How did the cosine squared theta minus cosine squared theta become cosine 2 theta?
That's the double angle identity for cosine. So I would say, if we're writing it as a function of theta and z, that would be the solution. If not, I want it fully simplified, what I highlighted would be, or you can just leave it like that. Rectangular as a spherical. Oh, bummer. If that was plus z squared, this would be really easy. No, but it's not. How can we write x?
B sine rho cos theta.
What was it?
B sine rho cos theta.
You said it wrong. Why did you say phi sine? That doesn't make sense. Should be sine phi, not phi sine. Remember, sine is a function. So you can think of it as an operator. It has to operate on something. What is y?
Rho sine theta sine
What is z?
rho cos theta.
That has to equal 1. Can we simplify that?
distribute that rho square?
Distribute.
Or sorry, square root, the whole thing? Take out the square.
The sine squared theta and cos squared theta, you can use them.
So you can't take the square, you can't just get rid of the square, just take the square root. Square root doesn't distribute across addition, only multiplication.
Sine squared theta and cos squared theta, you can simplify that into one.
I don't see it cosine squared plus sine squared.
Now you can factor out
There you go, that's the first thing you have to do. What are you factoring out?
rho squared sine squared theta, or theta.
Of what? What are you factoring it out from?
First two terms.
Can that be simplified further?
Yeah.
Yeah.
Factor out the rho squared.
Can that be factored down further? Or
Yeah,
not factored, simplified?
the double item,
For what?
sine squared, theta, and minus cosine squared.
Is that a double angle? Identity?
I don't know if it's a double angle identity. It might be an identity.
I thought that's what you said, double angle.
I could say that.
So is that a double angle identity?
I want to say yes, but I'm not too sure.
Technically, it is written no. But with a slight change, it is.
To rearrange the solution.
So addition will just give you one. But there's going to be no way to rewrite that as addition. So think back to the last one.
Oh, switch it.
How can you switch that order?
Negative.
Yeah, factor out a negative. So sine squared minus cosine squared would just be negative cosine of 2phi. That's equal 1. That would be fine. Again, typically, you'll see, you might see, write the relation in the form rho equals f of theta phi. Right, so I'm going to keep going. Rho squared negative secant 2phi, can that be written as rho equals a function of theta phi?
You do that.
That's what I'm asking, can you?
I'll say no.
Negative rho squared cosine of 2phi has to equal 1. 1 is positive, isn't it? Rho squared is always positive. That means negative cosine of 2 phi has to be positive, which makes cosine of 2 phi negative, right? Which means secant of 2 phi would be negative. Negative secant of 2 phi would then be what? Positive. I'm not taking the square root of negative, I'm taking the square root of positive. That's allowed. That would be your function. Right, so you have to be careful with that because you will see that a lot. Square root of negative function. That doesn't say it's a negative value. Right? That's saying it's -1 times the value of the function. If the value of the function is already negative, then that becomes positive. Right? The only time that wouldn't be allowed is if it was like -5. Oh dear. Rectangular relation, x plus y plus z equals 1 in spherical. What's x? In spherical.
Rho cosine theta sine theta.
What's y?
Rho sine theta sine theta.
What's z?
Rho cosine theta. Sorry, no, rho cosine theta.
Can that be simplified?
Yes.
How?
Factoring out rho.
Can that be simplified any further?
You can take out the sine from the first picture.
You could. That's going to be even with double parentheses, though. And in my view, that's not really simplified. But yes, that would be valid. Would you ever simplify it any further from there?
Oh, yeah.
From what you just said, no. Technically, we could simplify this. Use simplify lightly.
You could take out the sine phi.
Well, that's what you said. And then from there, there'd be nothing you can do.
Yeah.
From here, technically, there is. It's not really simplified in my view. You could use the product to sum identities on those first two terms. I don't think it's going to look nicer because that's going to involve now trig functions of sum of angles and actually half of sum of angles, which doesn't look nicer. And I don't think you're going to get terms to cancel out. If you do, you're not going to get all of those terms to cancel. You might be able to do some dark voodoo math to use some difference identities by adding inappropriate terms. Again, I don't, just from looking at it, I don't see that that would actually be simpler. So I would say, personally, that's my most simplified form. Technically, most simplified would be factoring out the row. But then that adds parentheses, and to me, that just doesn't look simple. So I would stick with that very first one and say there's nothing factoring out that row doesn't benefit me in any way. And I'm not going to worry about writing that as rho equals a function, because that's going to be a really hideous function. Cylindrical, r equals 2 sine of theta as a rectangular. What's r?
Is it square root of x squared plus y squared?
Theoretically, it could be plus or minus, but the argument actually isn't going to change if you do allow for negative. So I'm just going to assume positive. And you'll see why soon, why the plus minus doesn't change the argument. What's sine of theta? What does y equal?
R sine.
So what's just sine of theta? You just told me what y is. Solve that relation for sine of theta, what do you get?
Y over R.
But what was r?
Oh, so it's just 2. Oh. That's 9.
Wouldn't be y sine of theta. Be y cosecant theta, but that's not what I'm looking for.
Y over r.
What is it?
That's square root of
Yes.
X plus Y squared. Oh.
This is why the plus minus doesn't matter. Multiply both sides by that r. Since r is the same, they'd either both be positive or both be negative. And you get the exact same result regardless. We're going to keep going. Subtract 2y. Can that be simplified? Yes. How?
Complete the square.
Yes, complete the square. Specifically, for which variable?
1.
So what do you want to add to the y terms to complete the square?
Plus 1.
Which means you also have to add one to the other side. What's that curve? Be more specific. It is a circle. What kind of circle?
One that shifted down.
I would agree. You're still missing a key component.
Center on the positive y-axis.
Where? That's not center. Center has to be in order of pair.
Oh, yeah. 0.
Which is shifting. Still missing a key component of the circle.
Was where you
That's a radius 1 circle centered at 0, 1. That's the curve. But wait, this was supposed to be a cylindrical relation, which means it has to be three-dimensional. So what's the surface it represents?
Circle.
What's the surface that represents? Remember, surface is three-dimensional.
That's the top and bottom.
It's a cylinder.
It's a cylinder. Specifically, cylinder, right circular cylinder, remember, whose cross sections are circles that are centered at the point 0, 1 on an xy plane. Right? The xy plane itself is when z equals 0, and xy plane would be any plane parallel to the xy plane. Right, so it extends infinitely along the z-axis, but it's centered at 0, 1 on the xy plane with radius 1. So all of your cross sections are radius 1 circles centered at 0, 1. That would be what this surface actually represents, or what this represents, because we're dealing with 3D. So there are two ways I can proceed from here. I'm just going to do this and say that rho sine theta sine phi equals sine phi. Multiply both sides by sine phi. Now, what's rho sine theta sine phi in rectangular?
So why?
Just y. What's sine of phi? What's cosine of phi? How is cosine defined on the right triangle? What's that missing line?
The opposite.
Which is what? What's its length?
So or
What's the measure?
Z plus
It's going to be r, but I don't want r. And so ignore the fact that right now we're dealing with cylindrical coordinates, spherical coordinates. How did you get R?
Oh, I just looked at the coordinates that you use for cylindrical.
Yeah, that's fair. That's not what I'm looking for here.
Square root of z squared minus, no, rho squared minus z squared.
Which is R.
That's, okay.
So it's just like.
Well, if you allow R to be negative, it's not R, it's absolute value of R. But yeah, that's R. Which might be even more helpful, but that's what I'm going to do. Phi, what do we know about phi? What are the values phi can take?
You said it was anything or higher than 2. No, that's
0 pi. What do you know about sine over that interval?
Positive.
It's always positive. So the fact that cosine can be negative is irrelevant here and can just safely use the right triangle. Because sine will be positive regardless. Now, what's sine of phi?
square rho squared minus z squared over 8. Or over rho, sorry.
Which would be r over rho. Where r is the square root of x squared plus y squared. Right, because rho is, well, rho squared is x squared plus y squared plus z squared, right? So rho squared minus z squared is just the square root of x squared plus y squared. Oh, but wait a minute. R is just what? Square root of x squared plus y squared. What's rho? Was it? Rho squared root of x squared plus y squared plus z squared, right? That's your sine of phi. That nightmare. We probably could simplify that. Square both sides. Do some funny things. I don't see how that's going to benefit. So I'm going to leave it in that. So we wound up having to multiply both sides by an x squared plus y squared plus z squared once we square it. I don't see how it's going to simplify from there as something more recognizable, so we're going to leave it like that. Two things to point out. Where was the one I wanted? Here. No. Here. X squared plus y squared in spherical. we got to be rho squared sine squared phi with algebra. You may want to write that identity down so you don't have to keep doing it. In spherical, x squared plus y squared is rho squared sine squared phi. This way, anytime you see it, you can just jump right to that. And the second was this, that sine of phi is this. So you don't have to, again, redo all that derivation, because we just did it. That was what this was here.
Wait, could you repeat this for me? What was it?
Sine of phi is just that,
Okay.
that whole messy square root. And so again, those are two identities you might want to write down and keep handy. Maybe write it with your conversion formulas. So questions on those two coordinate systems? So again, pretty straightforward, but extremely important. On that subject, right? You're familiar with obviously the trig functions. Did you study the hyperbolic functions in Calc? The sinh, the cosh.
No, the H and I.
Yeah, that's for hyperbolic geometry. And so those are the trig functions on hyperbolic geometries. Yeah, there's also spherical trig. That's trig on a spherical coordinate system. Those are fun. Those are really fun. You're also familiar with one of the fundamental identities of a triangle, right? Sum of all the angles has to be what? Give it to me in radians. Yeah, that's actually only true in Cartesian. You actually lose that in spherical. You draw a triangle on a spherical surface, the sum of the angles does not have to be pi radians.
Is it curved, I guess?
There are other properties that have to be satisfied. I don't remember them off the top of my head because I never really. The only time I really studied spherical geometry was for my undergrad thesis. When I was doing a paper on the mathematics behind general relativity.
Wait, but how does that work? Even though if it's curved, wouldn't it still be?
There's no such thing as parallel lines either.
So like in like a spherical, like you mean like the points are like going.
In a spherical coordinate system, you do not have parallel lines.
Because like they're all like curved, right?
Okay.
That's the reason why the angles no longer have to sum to 180.
Oh, okay. So I was just
Right? Because
imagining-
weird things happen. The geometry you're used to is all Cartesian geometry, Euclidean geometry. When you go outside of that, you lose properties, but you gain different properties.
What do you use spherical geometry for? Like,
Everything. Technically everything. But it's really used in geometry because you have to look at the bigger picture. Right? The reason why we can get away with Cartesian in our physics is because if you just look at short distances, the curvature is negligible. So you can treat it as a flat surface, right? So this table we can treat as flat because it's such a short distance. Like when you're going a short distance, you can treat this flat even though the Earth is spherical. Because over that short distance, the curvature is so small, it's negligible. It's treated as flat. Right? So that's why we stick with Cartesian in every application. But when you start to get larger, you have to consider it to be curved. And again, that's why jump to you have to consider spherical. And it just sucks. Working in spherical sucks. Okie dokie, so get into your group. Such a giant group in this course. There's so many of them. So we'll work on this. This worksheet does the surfaces and the cylindrical and spherical. For 30 minutes, we'll say. I'll let it run down. We'll do a break. It should go. Actually, I'm still actually under. Supposed to go to. No, I was supposed to stop. 30 minutes will be 240. Time to break at 250. We'll pick back up for 25 minutes. We're going to start vector value functions. Here in close we get it. Everything we've been working with so far have been vectors where each component was a constant. So the next logical step is to look at vectors where the components are variable. It's called a vector value function. We're restricting our study to those where the component functions are real value functions of some parameter, typically t. Domain is the intersection of the domains of each component function. Right? Vector is only defined if all the components are defined. Taking the limit of a vector. Do you remember the formal definition of limit? That's for
Formal, you mean as in like, and what it means?
yeah, the actual definition of limit.
What it approaches.
That's the intuitive definition. It's an epsilon delta definition. Does that sound familiar? You said you had it for Cap 1, so it should sound familiar. Try to do over it. For all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus d is less than delta. Limit as x approaches d of f of x equals 0. That's the epsilon delta definition. What it says is you can get f of x arbitrarily close to L by choosing x sufficiently close to d. That's essentially what it means. This is the formal definition for the limit of a vector value function. Right, and then this part here is a function. It's a real value function, which you then plug into the epsilon delta definition. But that is not really useful in evaluating limits. Well, as it turns out, limit of a vector is just the vector whose components are the limits of the original components. So you just take the limit of each component, provided all the limits exist. If even one of those limits don't exist, then the overall limit does not exist. Right? remember the definition of continuity? What does it mean for a function to be continuous at a point? There are three conditions. So we say f of x is continuous at x equals a when three conditions are satisfied. What's one of those conditions? Do you remember? Be more specific, what limit? As x approaches what?
A.
So limit as x approaches a of x has to exist. That's actually the second condition. What's another one? Recap one instructor's crime rate. I'm going to make you retake cap one with me. FA is defined. Limit as x approaches a, f of x has to equal f of a. The exact same definition. Except you're now dealing with a vector instead. Right now, remember you had the different types of discontinuities. You had a removable discontinuity, which is if the first two conditions were satisfied, but the third condition wasn't. You had a jump discontinuity if the first condition was satisfied, but the second wasn't. And then you had an infinite discontinuity if the limit was infinite on either side. Find the domain and express it in interval notation, right? Remember, when dealing with domains, there are two ways to express a domain. Interval notation and set builder notation. Here they specifically tell us they want interval. First thing to do determine the domains of each individual component function. Starting with f. What's the domain for natural log of 11t? Making you think back to pre-calculus.
But you just said it was like
So let's just look at the general natural log function. Natural log of x, what's its domain? Open or closed?
Closed.
What's log of 0? Something to the 0 is what we use.
So it has to be greater.
Has to be larger than 0, so it's open. Log of 0 is undefined. Right, because that's essentially asking for natural log, if I just look at natural log, e to what power is 0? There is no power you can raise e to get 0. So we know that log of x is 0 to infinity. Well, now it's 11t. 11t has to be greater than 0, so what is t? Greater than 0. What's the domain for G?
Has to be greater than -10.
Larger than -10?
Or sorry. No.
So you can say this.
Zero infinity. Something t has to be greater than -10. It's just negative.
Square root of x, what's the rule? Can't be negative.
Yeah.
Is 0 negative?
No.
Greater than or equal to -10. You can take the square root of 0. Unless it's something complicated. Yeah.
Oh, I was just gonna say next one.
What's the domain of H?
11 or 11 to 8.
So at 12, where's 12 minus 12? There.
0.
That's not allowed.
So 11.
First, you 12, but like not including, right?
Oh, wait, 11 to negative 50. Because you can't go above the zero, it's going to be a negative number.
Bracket,
So again, at 12, you get 0, which you're not allowed to have.
oh, this
Because
is
it's a
a
denominator. At 13, what's 12 minus 13?
Negative
Is that allowed?
It's negative 50.
Like bring negative infinity to what?
So 11.
12 not including, right?
Wait, but wouldn't it do the same thing if I did 11 bracket?
11.5 is greater than 11.
Oh, I see what you're saying.
Domain of R is their intersection. So I'll break it out. What's the definition of intersection of sets? Remember, intervals are sets. So what's the definition of the intersection of sets? So we'll just do the simple one. A intersect B. Just look at two sets. What's that definition?
Should repeat that?
What is the definition of A intersect B?
All the select terms.
Formally, set of all points such that X is in A and X is in B. And then you can extend that to more than, in this case, 3 sets. Right, so it's the set of all points that are in common. If you look at Venn diagram, it's where they all overlap.
So it'd be infinity, turn on.
So infinity's not in all three.
No. I was just.
So it can't go to infinity.
Isn't it like negative 10 to 12?
Is negative 10 in the first one? Zero. Kind of the easiest way to look at it is what's the smallest value that all three have in common? In this case, open at 0. What's the largest value all three have in common? Then the open at 12. There's your interval, 0 to 12. That's the easiest way to look at it for intervals. This gives us a new way of writing parameterizations too, by the way. Vector value functions. Right? We don't have to just now look at a set of parametric functions, what we were doing before, right? X equals, Y equals, Z equals. We can now write it as a vector, which we just typically refer to as the parameterization. Right? So if you hear parameterization, it's always vector value function for you, which is exactly what's being asked here. We want the parameterization, the vector parameterization of a circle of radius 6 in the xy plane centered at the origin. And then we will verify that this is indeed a proper parameterization. Since we're dealing with a circle, I'm going to use theta as my parameter. But you don't have to, right? You can use anything you want as your parameter. So the circle is located in the xy plane. It's radius 6, centered at the origin. So let's imagine this real quick. Here's the xy plane. We're centered at the origin. Let's try and actually draw a circle, which is always fun. Symmetric. Yeah, good enough. That doesn't work. It's radius 6. Let's just pick a random point. XY. What is the x coordinate? In terms of theta.
These, yeah.
What's the y coordinate? What's the z coordinate? It's 0. It's located on the xy plane, which is z equals 0. However, that's not good enough. Always need a domain. Right, in this case, the domain's kind of implied. but in the future, we will need domains. So it's good to be in the habit of writing it down now. Technically, it's strictly less than 2 pi. You're not incorrect if you do this. You say less than or equal to 2 pi. That repeats a point, which is why, to be mathematically correct, you don't ever return to 2 pi. But I don't care either way, whichever one. When we get to actually needing these, you may actually have it equal to 2 pi as well. Right, that'd be a closed curve, because it returns to the starting point. But we'll cover that when we get there. Now we have to verify that this is a parameterization. Well, first, since we're on the xy plane, we have to have z equals 0, which we do. Perfect. Now, just to verify that what's remaining is a circle of radius 6 centered at the origin. What's the equation for that circle? What's the relation?
X squared plus y squared equals 6.
When we plug that into that relation, we better get 36. Back up to 36. You get 36 times 1. 36. And this is just a verify, so I'll just press my face. This is a parameterization. It's not the only one, by the way. But it's good enough for our purposes. Duplicate this at some point. Vector parameterization for the line through those 2 points, satisfying a list of conditions, right? So first we'll have to satisfy condition A, then I'll have to satisfy condition B, then I'll have to satisfy condition C. So to get started, what we're going to have if we just look at it, this would be the vector parameterization in general. X naught, Y naught, Z naught is any point on the line, and then the vector ABC is your direction vector. Right? It's a vector that is parallel to the line in question. Well, our direction vector would have to be PQ. 9 minus 4 is 5. -3 minus 1 is -4. 3 minus 1 is 2. Pick any point on the line. For 1 mark. And in fact, that t can actually just be any function t. Right? So it's supposed to be a scalar. Right? And then your t values just depends on what your function is. Right? To get the specific point, it'll just be different t values depending on what that function is. T is the easiest one, but it's not the only one. The goal is going to be finding that specific function of t for each of A, B, and C. That is the goal. Before I forget, I'm just going to go ahead and duplicate these. And I'll work with adjusting them later because I don't have time. We will finish this up on Monday and then move on to the next topic, right? The third homework due June 9th. Don't forget you have that group assignment. First quiz actually rolled now. He posted it, but it's probably already out. It'll be due before Monday's class. It does cover up through, not the vector value functions, up through cylindrical and spherical equivalents. And of course, the rules from the green reference sheet, I'll put that up there for every class. Have a great weekend. 2 of you, I'll see tomorrow. Yeah.
What is,
Yeah.
does the quiz list the topics that are on it, or is it a?
I don't believe so.
So I was gonna say.